in trig and used reducing radicals. So I don't know, some of you, this might be new for the reducing of radicals that aren't perfect squares. This is, you're multiplying two radicals together. So if you have the square root of 3 times the square root of 3, you can actually represent that as the square root of 9. So you're allowed to take the two items, multiply them together under one radical. So even though I can't take the square root of 3, I could actually take the square root of 9. And what is the square root of 9? Just the number 3. So when you multiply the same radical by itself, the radicals end up canceling each other out, and you just get 3 as your answer. So kind of the same thing on number 2. The square root of 2 is irrational. It's 1.4 something. And the square root of 50 is irrational, 7 point something, right? Because square root of 49 is 7. But I can multiply those together. Now it's magically the square root of 100, which I can take the perfect square root of, right, is 10. Square root of 100 is 10, because 10 times 10 is equal to 100. And what would number 3 end up being? The square root of 36 is 6. So see how sometimes it can help you evaluate a perfect square when there wasn't a perfect square. We are going to use this property a different way to write something in reduced radical form. And when you get to trig, if you haven't taken trig yet, sometimes you take trig before or after algebra 2. So when you get to either part of geometry or trig, you'll see reduced radical form a lot. So like the square root of 24 is not a perfect square, but that's also not considered reduced radical form because there's a perfect square that lives inside of 24. So you want to start thinking about all the perfect squares, 1, 4, 9, 16, 25. Which of those, 1, 4, 9, 16, or 25, goes into 24 evenly? 4 does, right? So I like to rewrite it as two separate factors, 4 times 6. And I put my special factor first because when I take the square root of 4, I just get a perfect number 2, right? So the reduced radical form of 24 is 2 root 6. I want to show you on a calculator. If I take the square root of 24, I get 4.89. If I take 2 times the square root of 6, I get 4.89. So see how they're equivalent to the same irrational decimal? One is just considered reduced radical form. So I'm just introducing it to you. You're going to be allowed to leave your answers in either decimal or reduced radical form on the test. But for the quiz, I might be asking you this skill just to start, processing this skill. So with 72, I have to go a little bit further. So 25, 36, 49, or 64. So which of these perfect squares, the biggest one, you're looking for the biggest one that would go into 72 evenly? Yeah, and some of you might say 9, because 9 times 8 is 72, but you want to find the biggest perfect square. So the biggest perfect square is 36, because 72 is 36 times 2. So my final answer for reduced radical form, the square root of 36 is 6. And then the square root of 2 is going to stay trapped under the radical. So what would you use for 300? What's a perfect square that's divisible into 300? It's even bigger than any of the ones I have in this list. 100. 100 times 3 is equal to 300. So what's my final answer in reduced radical form? 10 root 3. Yep. So that's reduced radical form. I show it to you because we're going to practice writing our answers in reduced radical form. But if when you get to the test you prefer decimal form, that's okay for this unit. You're going to have to do this in trig anyway. So I'm planting the seed for trig. So the reason I'm showing you a new method is because sometimes you might not be able to factor something. So this says taking the square root of both sides of an equation maintains equality. It's helpful when there's only x squared, not an x term. And when you take the square root, you have to make your solution plus or minus because there could be two solutions produced. So the example I give, if you're looking to solve x squared equals 4, the two solutions are positive 2 and negative 2 because 2 squared is 4 and negative 2, if you put it in parentheses, squared is also 4. So to solve this, you're going to take the square root of both sides. The answer is 2 or negative 2. So you end up getting two different solutions. The reason when we take the square root on a calculator, so the square root of 4 on a calculator just tells you that the answer is 2, right? That's called the principal square root. So if I'm asking you just, hey, what's the square root of 49? You all know that the square root of 49 is just the number 7. It's not also negative 7. Just the square root of 49 is 7. It's called the principal root of 49. But if I'm solving an equation, what number squared equals 49? The answer is 7 or negative 7, right? So if I'm trying to find all the solutions that satisfy this, there's two solutions. But if in a separate problem, I'm just asking you, hey, what's the square root of 49? You would just tell me 7 and you're correct. So there's a difference when you're talking about a variable and finding all possible solutions, or you're just taking a square root just for the sake of taking a square root on your calculator. All right, so here's before we do the actual practice of solving with square roots, why don't you try reducing these radicals first on the next page? Why don't you try 1 through 6, because this is that reduced radical form that I just showed you. So for each of these, I skipped a page, but for each of these 6, let's do this to practice that skill. You're trying to find 1, 4, 9, 16, 25, 36, 49. Do I have to go any higher for these? I don't think so. 64, 81, or 100. I think between those, the first 10 perfect squares, you can find what goes into these 6 numbers. You want to pick the biggest one. So I always start with the number 40 and I look backwards in my list. Okay, does 36 work? Does 25? Does 16? So I always work backwards in my list to make sure that I'm finding the biggest one. So let's do one more together. What would you say for the square root of 40? Right. 4 times 10 is 40. So I'm going to take the square root of 4 and I'm going to take the square root of 10, and 2 root 10 is my final answer. So see if you can take a couple minutes and try those 6. So let's see. Sorry, I forgot to send this. Where's my pen? All right. 98 was 49 times 2. Is that right? Square root of 49 is 7, radical 2. So again, all this means, and if you like taking the decimal answer, the square root of 98, the answer would be 9.9, right? But if I take 7 times the square root of 2, I also get 9.9. So it's just the reduced radical form. One reason why reduced radical form is nice is because it's an exact answer. If you're trying to get to the moon or you're trying to do microscopic surgery on someone with, like, you know, lasers for radiation, you want to be pretty darn precise of which cell, right? Or if you're going into outer space like thousands of miles, a tiny little decimal is going to make a big difference on a bigger scale or a tiny scale. So if you rounded this to 9.9, by the time you get to the moon, your angle could be off and you just miss your trajectory completely of what you're trying to get to. So sometimes it's easier to write the radical or the reduced radical form and keep all those decimal places so that you're not off by a lot, right? Because this decimal error, when you magnify it up, could mean a big difference, right? So square root of 125, the greatest perfect square was 25. Is that right? 25 times 5 is 125. Take the square root and you got 5 root 5 as your answer. So the first square root should drop out because you've taken the square root and you just get the whole number 5, and then the square root of 5 stays the square root of 5. All right, 150. That one's also 25, isn't it? It's just 25 times 6. So square root, you get 5 root 6. So your brain starts to get trained to see the perfect squares. Let's see, 120. 181, 64, 49. Does 36 go into it? No. And 25 doesn't. Does 16? It doesn't? Is it just 4? I have to go backwards and check. Okay, so yeah, it is just 4 because 9 also doesn't work, right? Because 120 divided by 4 is 30, and 30 doesn't have any other perfect squares. So you can kind of check for yourself. If 30 is the other factor, if 30 had another perfect square in it, then you know that you chose the wrong one. But 30 is fully reduced. So 2 root 30 is the final answer. And then the last one is 9, right? 9 times 3 is 27. So 3 root 3 is the final answer. All right, so you get the hang a little bit of finding answers in reduced radical form. So now we're going to take a look at example 1 on, let's use this method. So first of all, I want you to notice that sometimes quadratics are not equal to 0. Okay, so if you're going to use factoring, you always want it equal to 0 on this side, but we're using a new method, solving with square roots. I recognize that there's only an x squared on this side. See how there's no x terms? There's also only an x squared here. There's an x squared here. So see, all of these are set up for taking square roots. If there's an x, you don't want to take the square root of x. It's not going to help you. So your goal is to get x squared by itself. How do I get x squared by itself? Add 7 to the other side, which gives me a nice perfect square. It gives me 36. And then when I take the square root to get rid of the perfect square on this side, I get my two solutions, 6 or -6. Remember, because when you're solving for all the solutions, you want to make your answer either the positive or the negative of the answer. So we're not just looking for the principal root, we're looking for anything that makes this a true statement. -6 would also work. And if you wanted to check the answer on your calculator, make sure when you plug in -6, you put -6 in parentheses and square it, and then -7. See how that gives you 29? If you just do -6 squared, it's not going to give you the right answer because the -6 needs to be inside the square. All right, so the next one, how do I get x squared by itself? Divide by 5 on both sides. So if I divide by 5, what is 80 divided by 5? What do you get? 16, right? Is that what you said? So take the square root of both sides. X is either 4 or x could also be -4 because -4 squared is also 16. So those were one-step equations. I had to add the 7 to the other side. I had to divide both sides by 5. Number 3 is going to be a two-step equation. What would I do first to get x squared by itself? Subtract 5 is my first step. So I have 3x squared equals, that would be 36, right? What's my next step to get x squared by itself? Divide by 3. So x squared equals 12. So now this is where that reduced radical form is going to come in. Now I have to simplify the square root of 12. So I'm going to write x equals plus or minus, because remember there's always two solutions. Let's see, what are the factors for 12 up here that I'd want to pick? 4 times 3 is 12. So when I take the square root of 4, I'm just going to get 2 root 3. So my final answer would be x equals plus or minus 2 root 3. If you want to write it as 2 root 3 or -2 root 3, that's the same meaning. Plus or minus is just like the shorthand. All right. on to example 4. This one looks a little bit different. This one you might want to distribute the squared and multiply the binomials. So resist doing that because right now you actually have just x squared. If you multiply this out using the box method, you're going to get an x term, and then you can't solve it with square roots. So this is what you're going to consider your square. So you want to divide by 2 to start the problem so that you get the perfect square by itself. X minus 2 squared equals 20. So now your next step is to take the square root of both sides of the equation, which might feel a little bit weird with the parenthesis, but the square and the square root just cancel each other out. So you just get x minus 2 left. You don't actually do anything to the x minus 2. Equals plus or minus. How do I break up? The 20? What's my perfect square that's in the 20? Reduced radical form. Yep, 4 times 5. So take the square root of 4. This is the hardest one to write the answer to, I think. 2 root 5 is the reduced radical form. And then what would be my last step to get x by itself? I still need to add 2, but I'm not going to add 2 to the radical because 2 is not a radical itself. It's like a constant. So think of this almost as a variable. This is not a like term. So x is equal to plus or minus 2 root 5 plus 2. So that's just the jumbled up answer in radical form. If you wanted to find the decimal answer, that's also fine. You could just take the square root of 20 and then add 2 to it. Square root of 20 added 2 is 6.47. So if you like the answer 6.47 better, let's see, what's negative the square root of 20 plus 2, or negative 2.47? This is just the reduced radical way of writing those two decimals. So if you really hate reduced radical form, all we're trying to find is the x-intercepts. But the reason that these are not factorable is because, hey, these didn't come out as integers. All right, last one together, and you're going to try some guided practice, and I hope this method is kind of a one day and done. We feel okay with it, and then you could try homework 4-5 tonight or tomorrow. What would be the first step? I'm going to get x plus 3 squared by itself. So what would you do first? Add 32 to the other side. So now I have 2x plus 3 squared equals 32. Yep, so your second step would be to divide the problem through by 2. So you'd have x plus 3 squared equals 16. So what would your next step be? I have the perfect square by itself, right? So what do I do to both sides? I take the square root of both sides, and then I just get x plus 3 left by itself. And 16, the square root, is just 4. So it might be easier over here to write 4. 16 is a perfect square, right? So the square root of 16 is just 4. So this is one of those times I don't need reduced radical form because it was already a perfect square. I wrote 4 or negative 4 separate because when I subtract 3, to me it's easier to just get your two answers at this step, right? So if I subtract 3 from positive 4 or I subtract 3 from negative 4, I'll get my two solutions. So my two solutions are 1 or negative 7. So that one actually should have been factorable, but it was not given in factorable form. So I would like you to try. There are 6 problems on the next page to see how you do with solving by taking square roots. One thing I want to throw in there, can you take the square root of a negative number? So if you perhaps have to take the square root of negative 10, it would be no solution. right? You cannot take the square root of a negative number. Now on number, where did I just see a negative number? Like number 12, this is not going to be a negative number in the end because you're going to add 23 to the other side and actually get 0. Can you take the square root of 0? Yes, the square root of 0 is just 0. So just be on the lookout in case anything comes out as a negative number. You cannot take the square root of a negative number. It would just be no solution. So I'm going to put it on the video. I think most of you finished, but wait a second. Oh yeah, so we got plus 2. So x squared was equal to 44. And then when you took the square root of both sides, you said 4 times 11. So x was plus or minus 2 root 11. And I looked at your papers and it looked like you pretty much got that one right. The next one added 32 to the other side. This was actually very similar to the one we already did, wasn't it? Oh, it was the same as example 5. Whoops. I was looking at your answers and I thought it looked very similar. So 32 divided by 2 gives you 16 over here. You take the square root of both sides. X plus 3 is 4 or negative 4. So when you subtract 3, you end up with positive 1 or negative 7, right? This one came out to 75 on the other side. X minus 1 squared is 75. So when you took the square root, x minus 1 was, what's this? 25 times 3 is 5 root 3. And then to finish the problem, you just add 1 to the other side. So plus or minus 5 root 3 plus 1. 10 comes out to no solution. I think you recognize that when you subtract 80 to the other side and divide by 2, x minus 1 squared is negative 40, and you cannot take the square root of negative 40, so there's no solution. The graph of this quadratic must have no x-intercepts. So on 11, to divide by a fraction is the same as multiplying by the reciprocal, so that you get x plus 3 squared equals 20. So then you can finish this one the same way that you normally would. Square root x plus 3 is plus or minus, let's see, 20 is 4 times 5. So 2 root 5, and then you'd have to write the minus 3 on the other side at the end. And then 12 is a special example we're going to see a little bit more of on Monday. It only has one solution because you get x minus 1 squared equals 0. When you take the square root of 0, you only get one solution, 0, because plus or minus 0 is still 0. So then when you add 1 to the other side, the only x-intercept is at positive 1. And we're going to see that there's a special case for this with the quadratic formula on Monday as well.